Welcome back to another riveting installment of our pre-calculus journey through Unit 1. Today's content is on equations, and more equations. Clearly, you can see there's a considerable amount of vocabulary for you to work through. We're going to be talking about linear equations, quadratic equations, rational equations, and kind of reinforcing some of that fluency that might have gone to the wayside since it's been quite some time solving equations. So today we are learning to compare and contrast quadratic equations with real and non-real complex solutions, and that'll be our next lesson. So I can solve quadratic equations and explain the solution method. I'll know I've got it when I can explain in writing the reasoning used to solve a quadratic equation by completing the square and by using the quadratic formula. Let's get to it. Let me move my little pen tool. An equation is a statement that two mathematical expressions are equal. A statement, two mathematical expressions equal. The solutions or roots of an equation are the values of the variable make the equation true. We call two equations with exactly the same solutions equivalent equations. And since it's been quite some time, but being in pre-cal, there's kind of like this implicit assumption that you're a equation solving machine. So I'd like for you to share your thoughts with your classmates about how you would go about solving an equation. In both of these instances, these are some of our properties of equality. I would like for you to once again take a moment to take a look at our initial statement, A equals B, and describe what is happening to the equation. How are we manipulating it algebraically? And take a look at what I've said down here, right? These properties require that you perform the same operation on both sides of an equation when solving it. Mathematics has always been a trailblazer in society. We've been advocating for equality since the dawn of time. You might remember this phrase growing up where, an older brother, sister, parent, teacher, authority figure would always tell you to treat others how you want to be treated. Well, equations have been doing that for millennia. We've always treated one side of the equation the same as we've treated the other. Don't start changing things now. All right, so just give us a quick description using some arithmetic operations that you see with your eyes, and we'll take it to our first set of specific equations, that being a linear equation, which is a equation where, don't want to say in which multiple times, where each term is either a constant, right? So something like y equals 3, or a variable to the first degree. Linear equation in one variable and is an equation equivalent to one of the form ax plus b equals 0. So here's our constant b because there's no variable attached to it. And we have a variable term here that is to the first power because we don't see one explicitly written. A and b are real numbers. Here, please solve the following equations. I haven't done any of these checkpoints so far because this is definitely some very straightforward information in terms of what you're expected to be able to recall for pre-calculus. If this is difficult, no worries. Let's look to meet one-on-one and kind of brush up any type of weaknesses you are having. Be very careful with B. Okay, we're solving for H. So we want to rewrite this equation so that it's in the form of h equals some algebraic expression. And now we enter the world where things have gotten just a tad bit more complex. Quadratic equations are second-degree equations. A quadratic equation is an equation of the form ax squared plus bx plus c equals 0, where a, b, and c are real numbers with a not equal to 0, because if a is 0, then that x squared term does not exist. Therefore, it becomes a linear equation. Okay, so a must be a value that is not 0. The zero product property says that, AB equals 0. You might be like, AB, right? If and only if A equals 0 or B equals 0. Okay. So in the previous lesson, we kind of spent a little bit of time reinforcing this idea of factoring. Factoring is a solution strategy that we employ when solving equations of the second power. So quadratics, we also use it with higher degree functions, but typically with quadratics, we're going to factor exclusively. So this means that if we can factor the left-hand side of a quadratic or another equation, i.e. a third degree, fourth degree, fifth degree function, then we can solve it by setting each factor. And sometimes the factor might be one singular term. It might be, typically, it's an algebraic expression equal to 0. This only works when a quadratic, I don't like using the word works. This is only applicable when a quadratic is set equal to 0. If it's not set equal to 0, factoring is not applicable. However, we do have a special case when we have a quadratic set equal to an individual value algebraically. We can simply take the square root. It's going to equal the square root of c and negative square root of c, right? Because remember, a quadratic is really parabolic, right? So it has that curved type of behavior. And if we draw a horizontal line through a quadratic, it should intersect 2 times. Quadratic equation does not factor readily. Then we can solve it using the technique of completing the square. And this is probably where most of you kind of go, in the what? So let's take a very in-depth look at part B. Part A, I shall leave for you. There's a very straightforward way to solve it, and there's a very convoluted way to solve it. That's up for you and your intuition to determine. All right. So here we go. In part B, I am going to subtract 24 from both sides. Therefore, my new expression looks like this. And as we had reviewed in the previous lesson, if we wanted to determine how to factor this, we are looking for 2 terms that multiply to negative 24, right? But add or subtract to positive 5 because the coefficient of x squared is 1. Those 2 terms are 8 and 3. So we're reverse engineering like the area model that we had first talked about. So in this case, we would have x plus 8 and x minus 5 equivalent to 0. And just as the zero product property said, right, we have 2 expressions being multiplied together. So in order for their product to be 0, one of them must be 0. And in this case, its values include negative 8 and 5. If you wanted to go ahead and take a moment to take this function and substitute it into Desmos, you'll notice that at these x coordinates, this is where the graph is equivalent to 0, or the x-axis, because that is when the y value is 0. So hopefully that refreshes your memory and can help jog what you're supposed to do for part A. But the real meat of our video is here. So I'm not going to read it all. You should probably pause the video at this time, read your way through it, okay, and determine whether Elena or Han or both have the correct solution. Okay. That's all I'm going to say, because this is kind of a think question, and I would like for you to share what your thoughts are. When you make your selection, you'll be asked to explain, so please try to be as specific as possible. Okay. And before I forget, okay, what Elena is doing is, because I forgot they don't mention it, this is our complete, what is going on with my pen today? Complete oh my goodness. The square. I'm gonna put dot dot dot. Must be having a case of the Mondays. So in slide 9, and yes, this is a pretty lengthy activity. I am giving you some time to work your way through some of these quadratic expressions. Okay. Some are very straightforward. Case in point, something like x squared equals 38. Some are a little bit more difficult, x squared minus 10x plus 25. And some require you to employ either the quadratic formula, which was listed on the previous page, or the complete the square technique. I think both are applicable. I prefer to complete the square because it's much more intuitive, but some of you might prefer quadratic formula because it's very formulaic, cut and dry. So 1, 2, 3, 4, 5 practice problems here for you to determine. I'm going to build in a self-checker. That way you can see how many you've gotten correct. Does that mean you can guess and check? Yeah. But at the end of the day, you're kind of only changing yourself. So strongly encourage you to work through these. If, for instance, one is not working out the way you'd like for it to, we can definitely review that. So there's definitely specific situations where we would rather complete the square rather than do the quadratic formula, and vice versa. What is your intuition telling you now that you've had 5 practice problems to work your way through? Let us know. There's no right or wrong answers here. Once again, you could definitely use quadratic formula for solving every quadratic you come across. You could definitely use completing the square for solving every quadratic formula you come across, quadratic equation you come across. But it really boils down to your intuition and your level of comfort regarding your solution strategies. Now, this is something that's going to come up much more later on in our course, but it's definitely a good time to talk about it. So within the quadratic formula, like we see here, we have, or Kieran notices that this value here within the square root, if we were to simplify, becomes negative 20. So he makes this conjecture that because that square root is negative 20, the equation is not going to have any solutions. What does that mean? It does not have any solutions. Okay? If you agree, select yes, share your thoughts. If you don't agree, select no, and share your thoughts. Yep. 1 second. All right, so we're almost at the very end, and I know this has been quite a journey for this video, so you're probably fatigued beyond belief at this point. However, we must discuss other types of equations. So when we solve an equation that involves fractional expressions or radicals, we must be especially careful to check our final answers. When we solve an equation, we may end up with one or more extraneous solutions. What does that actually mean? Okay. Extraneous solutions are potential solutions that do not satisfy the original equation. You often see this in issues of square root, radical functions, rational expressions, right? Because those are, just like in the previous activity or previous lesson, equations in mathematics that have restrictions on their domain, right? Radicals are unable, square root radicals, even root radicals are unable to be negative, okay? So we should resubstitute our solution into the expression to determine if it's applicable. So for quadratics on the previous slide, we have just seen that the b squared minus 4ac, oh, it disappeared my writing. Oh, there goes that. So this component here, which is what we refer to as the discriminant, because I don't really mean to be discriminating. Discriminant informs us whether or not our quadratic will have real solutions, non-real solutions, or no solutions altogether. So if you answered the previous question and you said yes, you're incorrect. But we have already seen that if b squared minus 4ac is negative, then the equation has no real solution. But in the complex number system, which will be the topic of the next video, this equation will always have a solution. Which brings us to something like part B. So in part B, I would want to make sure that my radical is isolated. So what I can do is I could bring the radical over in order to make it positive and bring the 2x to the right side. So that way the radical is completely by itself. So let's do that. So we would have the square root 2 minus x equals 1 minus 2x. Now to undo algebraically a radical expression, we would want to raise it to the second power. However, I think slide 3, right, we reinforced that whatever we do to one side of the equation, we should do to the other. So I'm skipping a lot of the work here, but the radical and the exponent will undo each other, and I'll be left with 2 minus x equals, I would offer you to expand this expression using the area model, but 1 minus 4x plus 4x squared. I have a quadratic, so I should collect all of my terms on the same side and set it equal to 0. Therefore, I would be able to factor it. So the final expression, 4x squared minus 3x minus 1 equals 0. Factoring this is a little bit of a doozy because we have a leading coefficient that's not 1. So I'll invite you probably to pause the video at this point and make your attempt at factoring this expression for viewing my solution, which would be 4x plus 1, x minus 1. You should probably go ahead and double check my math because I would never trust a math teacher. And our solutions would include x equals a negative 1/4 and 1. So I would just want to double check and make sure that both of these solutions are not extraneous. So if I substitute 1/4 in for x underneath the radical, I would get 2 1/4, which is totally okay, it's positive. And 2 minus 1 would yield a 1, which is also okay. So both of these solutions are applicable, and we would not define them as extraneous. That may not hold true over here for A, as we have a decent amount of algebraic expressions in the denominator. I apologize for that video being so lengthy, but that is where we will pause and pick up together in class.